Today, STAT students, we're going to go over section 9.1, performing a hypothesis test. So at some time, you may have learned about the scientific method, maybe in some sort of science course or what have you, and you've talked about it. And here's the thing: is that maybe you did some simple math, but you didn't do any complicated math or anything like that, or you didn't get too deep into the math. And the reason why is because actually statistics is actually the mathematical backbone to the scientific method. And so what we're going to do here is we're going to go through the steps of hypothesis testing, okay, and literally go step by step with you through this, all right? But basically, statistics is the mathematical backbone to really the scientific method. So there's two hypotheses. You have the researcher's hypothesis, and then you have the opposite of the researcher's hypothesis. And here's kind of the interesting thing, is that in order to prove the researcher's hypothesis to basically be true, he or she needs to actually disprove the opposite hypothesis. So you see this a lot in science, you see this a lot in philosophy, is that you don't actually, even though you have the researcher's hypothesis, you don't try to prove that one as being true. You try to actually prove the opposite, okay, of the researcher's hypothesis. And so if we could say that this is probably wrong, what does that mean about the researcher's hypothesis? That's probably correct, okay? And so that's what's happening here. So you disprove one hypothesis based upon a random sample, and if you can do that with a certain amount of, you're going to use probability to do that, so with a certain amount of certainty, okay, that tells us that a lot about the researcher's hypothesis at that point. So the tests that we're going to conduct are called hypothesis tests. Now you might hear this being called in another class significance test. Same thing, same exact thing, it's just different name, okay? Hypothesis test, significance test, same thing, but I'm going to be calling it hypothesis testing. So a hypothesis test has 5 steps. 1, you state the hypotheses. 2, you go ahead and confirm conditions. 3, you're going to calculate a test stat. 4, calculate what's called a probability value, which because we put this on a computer screen, we don't like to write out the whole word probability value, so we shorten it to p-value, and then state the conclusion. Alright, so a hypothesis is a statement about a population. Remember what I told you on day 1. What is the researcher's main focus? It's about the population, okay? And we use sample information to understand the population. So so what's going to happen in here is that we're going to go ahead and create some sort of statement about a parameter. Now, where do parameters come from? They come from populations, right? And so we're going to make some sort of statement like P is equal to 30%. So the population proportion P is equal to 30%, or maybe mu. We're going to put mu in there is equal to, I don't know, say 5 or 3 or something, right? And so we'll figure out how to do that here in a little bit. It also what we could do is that we can make a statement where P is greater than 30% or mu is greater than 3. Okay. So the main goal in many research studies is to check whether the data supports the researcher's hypothesis. But how are we going to do that? We're going to go ahead and test the opposite, okay, of the researcher's hypothesis. So each hypothesis test has 2 hypotheses. 1, the null hypothesis is a statement that the parameter takes a particular value. It has a single parameter value, all right? Then we have the other hypothesis. The alternative hypothesis states that the parameter falls in some range of values. Okay. All right, so let's talk about the null hypothesis. The null hypothesis usually represents that there's no effect. Okay, or not alone that there's no effect, that it could be like the status quo of something. For instance, we're going to test here in a little we're going to have a hypothesis here in a second. You know, we typically think as the average temperature of a healthy human is 98.6. Okay, it's kind of the status quo. All right, so what we think is maybe already going on. Well, we can test against that. Okay, just test against the status quo, and so that could also go into the null hypothesis. All right, and so because it has this idea of no effect in it, okay, nothing or zero in mathematics is that's a zero, a null. Okay, so that's why we call it the null hypothesis, and the symbol that we give it is h sub zero. So null meaning empty or zero, that's why we give it h sub zero. So it's really important that you know that terminology, that the null hypothesis is h sub zero. In Chapter 9, the way we're going to go ahead and state the null hypothesis is that it'll be some sort of parameter like mu or population portion p, and it's going to be equal to some value. Okay, so for instance, we read the problem and we eventually figure out that we're working with means and that we want to set the null hypothesis equal to 10. So that's the first hypothesis. How about the second one? So we have the alternative hypothesis. This is usually where the researcher's hypothesis go, and it represents usually an effect of some type, that something is there. Okay, so the symbol for the alternative hypothesis is h sub a. H sub a. Now this is the symbol that this book uses, is h sub a. Other books will use h sub 1. Now don't freak out if you get into another course and they use h sub 1 for the alternative hypothesis. They're interchangeable, h sub a and h sub 1. Okay, now this book uses h sub a, so that's what we're going to use from now on. So the alternative hypothesis will have some sort of parameter, same parameter as the null, and it's either going to be greater than, less than, or not equal to the same value that you saw in the null hypothesis. And so, for instance, maybe you'll see, maybe we read a problem and we say, oh, we got to go ahead and set the null, alternative hypothesis to mu is greater than 10. All right. So what we're going to do is we're going to go through some examples here of setting the null and the alternative hypothesis. And once you learn how to do that, you have step 1. And that's basically what I said there. Now, before we actually practice it, excuse me. Before we actually practice it, what I want you guys to know is that in a real life study, in a true study, all right, the hypothesis should always be formulated before viewing or analyzing the data. Okay, you should already have done that, and so basically the researcher should state the hypotheses first, go collect the data. Okay, and then run through the hypothesis test. Okay, you don't look at the data, then formulate your hypotheses. Okay, that's backwards. Okay, all right, and so you always want to state your hypotheses first, collect your data, run through the hypothesis, and let's see what the random sample says about the hypothesis that the researcher has made a claim about. All right, so here's some examples here. So a researcher believes that the mean temperature of all healthy humans is less than 98.6 degrees Fahrenheit. Okay, and so here's the thing: is that when you write these out, the null is always written first. That's what we do in stats. Okay, the null is written first, and the alternative is written second. So the researcher's hypothesis, the alternative, all right, is written second. However, this kind of the strange things about it is that when you do these problems, when you read it, what's going to be stated very directly first is the alternative hypothesis in the problem. All right, and so a lot of times when we do these problems, I like to state the alternative first and then go back to the null. All right, and so what do we think here? So the researcher believes that the mean temperature of all healthy humans, and so since we're working with a mean, what are we working with? We're working with mu. Okay, and so basically what's going on here is the way you got to think of this is that mu stands for something. It stands for the mean temperature of all healthy humans in this particular problem. And so instead of writing all that out, because it can get very long, okay, we just go ahead and use a symbol for it. All right, and since we're talking about means, we're talking about mu. All right, and what does the researcher believe? That mu is what? Less than 98.6. And so that's what you would put into the alternative hypothesis. Remember, researcher's hypothesis, the alternative, mu is less than 98.6. Then we go back to the null, which is actually supposed to be written first. And so what are we going to do? We're going to put the equal to sign in there. Okay, so the null is written as mu is equal to 98.6. And that's it. That's step number one. So the null gets the equal to sign. The alternative gets either less than, greater than, or not equal to, and it just depends on what is the researcher trying to check. Okay, so before we leave this, whenever you have a less than sign in the alternative hypotheses, this is what we call a left-tailed test, a left-tailed test, all right? And so that's going to play a part later on when we do other steps. So less than sign, left-tailed test. Sometimes it's also called a lower tail test, all right? Left-tail test. So I just wanted to emphasize that, and there's the sentence for it, okay? Next example. A newspaper editor believes that a particular candidate will receive more than 45% of all votes. Okay, so now we're working with a percentage or a proportion. Since we're working with percentages or proportions, what are we going to be working with? We're going to be working with the population proportion P, aren't we? And the editor, which is the researcher here, more than, thinks that some particular candidate will get more than 45% of the votes. And so we're working with P, we're working, looks like a greater than sign, and what? 45%. So there is our alternative hypothesis. P is greater than 45%. Now you can also put P is greater than 0.445. So you can write it as a proportion or a percentage, either way. But I'm just going to tell you now is that when you put it into your calculator, you can't put it as a percentage. Okay, you got to put it in as a decimal. So a lot of times I'd like to write it as 0.45 right away. Okay, to remind students, hey, that's the way it's got to be put into your calculator. I'm going to get this because I know what's going to happen here. So let's go back to my pen. So what's the null going to be? The null is going to be P is equal to 45%. Now it could also be put as P is equal to 0.45, interchangeable. So if you want to start as a percentage, that's fine, okay, but do note that you got to put it in your calculator as 0.45 eventually, all right? Because the alternative has a greater than sign, this is what we call a right tail test or an upper tail test, okay? Right-tailed is the upper tail, all right? Greater than sign. So greater than sign, right tail test. Example 3. A professor believes that the mean time all college students spend studying per week has changed from 20 years ago when it was 10 hours. So here, this is a little different. Has changed. So the researcher doesn't care that it's less than 10 hours. It doesn't care. The person doesn't care that it's greater than 10 hours. It's just changed. So we want to see any kind of difference. And so when the researcher is trying to figure out any kind of difference from a particular value, what do you think that is in math? That is not equal to. And so the alternative is mu is not equal to what? 10 hours, right? 10. What is the null going to be? Mu is equal to 10. Why is it mu again? Because it's mean. So mu stands for the mean time all college students spend studying per week. Okay. So when you see a problem that says has changed, is different, not equal to, we're talking about not equal to. Okay. Any kind of good synonym for has changed. All right. Is different. Because the alternative has a not equal to sign, this test is called a two-tailed test, and we are testing, and this is important, we are testing both greater than and less than at exactly the same time. Okay? We are testing both greater than and less than at exactly the same time. All right? This is what we call the two-tailed test. I'm going to skip over the conditions because the conditions are very specific to specific hypothesis test if you're testing population proportion P or if you're testing mu. And so when we get into 9.2 and 9.3, we'll talk more about verifying conditions. All right. For now, we'll go to step number 3, testing the test statistic. So a test statistic describes how far the point estimate, so point estimate like p hat, remember point estimates are values of a statistic, and so things like the values of p hat or x bar, so things that are coming from our random sample, right? So a test statistic describes how far the point estimate falls from the parameter value that's in the null hypothesis. And how far away? Well, what have we been using as a unit of measurement? Standard deviations, or in this case standard errors. Okay. So if the test statistic falls far, really far away, and what's far as test statistics go? Like, we don't expect it to be more than, say, 2 standard errors, 2.5, 3. You're getting kind of far away, right? Certainly 3.5 and 4 is very far away as far as standard errors go and standard deviations, right? So if the test statistics, so things like x bar or p hat, falls far from the value in the null hypothesis, okay, it is evidence against the null and in favor of the alternative hypothesis. So remember, we test the null hypothesis and we compare it to our sample. So if our x bar is really far away from the value in the null hypothesis, well, that's telling us that probably what's in the null hypothesis, that statement is wrong and the alternative is correct. And the same would hold true for p hat in the population portion P if you're testing a proportion. We'll get more into the test stat specifics in 9.2 and 9.3. All right, we're going to have to calculate that, and we'll define it as we do certain problems. Okay, we'll define it even better in those problems. Step 4, probability value, aka the p-value. All right, so again, we like to put the probability value. We actually, every time you run a hypothesis test on a computer, it's always going to give you the probability value, but since this is such a long statement, we shorten it down to p-value. Okay, and this is not the same as p or p hat. Okay, that's why I want to stress this is something different. It's the probability value, and we're just shortening it, the wording, to p-value, so we can put it on a computer. Okay, but it's not p or p hat. All right, so using the value of the test statistic, we calculate the probability of getting that particular value, or more rare than that, assuming the null is true. We call this the probability value, and we shorten it to p-value. And even some computers will just put capital P, knowing that you ran a hypothesis test on the computer, that you should know that just the big old capital P stands for the p-value because you're looking for it. Okay. So I think what we probably need to go over is assuming the null is true. That statement sometimes confuses students. All right, and so let's talk about that a little bit. What does it mean that assuming the null is true? Well, you know what? Instead of getting to that slide, I got to remind you of something. Okay, remember when we were working in chapter 7 and we were working with the sampling distributions of, say, p hat. Okay, and what did we find out was the center of the sampling distribution of p hat? We found out that it was the population portion P. Okay, so the null hypothesis might have a statement like this: the null is set to P is equal to, say, something real simple here. Let's say something like 0.3. Okay, so what happens for every hypothesis test is that we temporarily assume the null is true. Okay, so if we temporarily assume that the null is true, what we're saying is that we're saying temporarily we're going to set truly the true population portion P 0.3. So what does that mean? We are temporarily setting 0.3 into the middle of the sampling distribution of P hat. So what do we do then? We sample and we get our P hat. Maybe remember our P hat is the sample proportion, and so we go ahead and calculate our P hat, and maybe our P hat turn out to be way down here. It turned out to be like 3 standard errors, 4 standard errors away or something. Okay. Now, do we expect our P hat to be really far away from the center of the sampling distribution? Hopefully, you guys say no. Okay. And so, if we took a random sample and our P hat is really far away from this temporarily assumed value for the center, what does that mean about this temporarily assumed value? It's probably what? It's probably wrong. Okay. P is probably not equal to 0.3, all right, because it should be, these two things should be what? Closer to one another. And that's the idea behind hypothesis testing. I can change all these values and put in the sampling distribution of X bar instead of P hat, and the center would be mu, and go through exactly that same example for mu, all right? So basically, if P hat is really far away from the value in the null hypothesis, and 2.5, 3.5 standard errors away, well, that means the value in the null is probably wrong. Okay, and if the value in the null hypothesis is wrong, what does that mean about the alternative? It's probably correct. That's the idea. So this slide right here sort of illustrates it. Here's a sampling distribution of some sort of test statistic. It doesn't matter what test stat you're probably working with. Okay, it's probably where a lot of times it's going to go, the value in the null hypothesis will probably be somewhere in the center here. Okay, so we put it the null hypothesis right here. All right, so here this is the sample value. This is the value of the test statistic. So like P hat or X bar, what have you. Okay, and so the P value is getting something as rare as this, or more extreme than that. Okay, and so believe it or not, calculating the p-value is pretty simple. All right, and we're going to go over the specifics of that in 9.2. Okay, I promise you that. What you have to learn, absolutely. Notice I put here 5 stars. There's another thing that has 5 stars. I mean, all this is important, but if there's ever anything to take away from this course and bring into another course if they're going to run a hypothesis test, is this right here. Is that the smaller the p-value, okay, the stronger the evidence that the data provides against the null hypothesis. So if our sample statistic like p hat is really far away from the null hypothesis, that means we're going to get a large test statistic, okay, in magnitude, and so it's like 3 standard errors away in either direction. All right, and that's going to lead to small p-values. All right, and so the smaller the p-value, the stronger the evidence against h sub 0, and that's telling us that the alternative is probably correct. Okay, the researcher's hypothesis. So what happens here is that when we run through the test, if we have a small p-value, okay, that indicates to us to reject the null. Okay, what does it mean to reject something? We think the statement in the null is incorrect, and if we think that the null is incorrect, that means we think the alternative, the researcher's hypothesis, is correct. Okay, and so you're going to see the statement a lot of times when we do our conclusion. So you might ask, well, how small does the probability, this p-value, have to be in order to reject the null hypothesis? By the way, before we leave the idea of the p-value, p-values are a probability, and so they have to be between what? 0 and 1. So if you ever get a negative p-value, you've done something wrong. If you ever get a p-value that's greater than 1, you've done something wrong. It has to be from 0 to 1. It is a probability. Okay, So we have this idea of the significance level, and it's stated directly in the problem. The symbol that we use for the significance level is alpha. Now, the reason why we have why we have to talk about the significance level with the p-value is that this is basically our cutoff. And what I mean by that is that it's the this is how low the p-value has to be in order to go ahead and reject the null hypothesis. And so usually alpha is going to be stated as 0.1, 0.05, or 0.01. Okay, those are typical values for alpha, the significance level. And now the most common one in practice, in a real study, is 0.05. And this again is set as an industry standard. Okay, the industry's figured out where to set alpha, and that industry will always use that particular alpha. But in the problems that we're going to do, we're going to move these around just to make sure that you have the idea. Okay, and this gets 5 stars, just as much as the other one. So, I see that this is supposed to have a less than or equal to sign down there. Sorry about that. So if the p-value is less than or equal to alpha, you're going to go ahead and say reject the null hypothesis. Learn that ASAP. Small p-values means to reject the null. How low? If the p-value is less than or equal to alpha, you're going to reject the null hypothesis. You absolutely positively have to know that. Go learn that statement right now. Get it in your brain. Burn it in your brain now, okay? Because we're going to test it over and over and over again, okay? So for example, let's say that we go through a hypothesis test and the p-value turns out to be 0.023 and alpha is set to 0.05, okay? And so you got to evaluate this decimal versus that decimal. And I know sometimes students have problems evaluating this, and so really, you should just be looking at basically the second decimal here. So if you have problems evaluating decimals, no matter how many decimal places we have the p-value, just take a look at the first two and compare it to this. Notice 0.02 is what? Less than 0.05, and it really wouldn't matter what's after this. Okay? The only time that it would matter is that if this was actually 0.05 and then some values after it, then okay, 0.05 blah 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 is going to be higher than 0.05. But as long as the second number right here isn't 5, okay, you can just pretty much ignore the rest of these values if you have trouble evaluating decimals, and just look at the first two decimals, all right, and compare them, all right. So some people have problems with that, all right. So in this case, since the p-value is less than alpha, we're going to go ahead and reject the null, and we think that the statement in the alternative hypothesis is true, meaning we think that the researcher's hypothesis is correct. So what we're going to do in 9.2 and 9.3 is we're going to test the population portion P and go through some more specifics there. And also in 9.3 we'll go ahead and test mu. Thank you for your time.